Hello and welcome to section 1.3 Evaluating Limits Analytically. And so in this video we are going to go through all the properties and things that you need to know and make sure that you get them down so that when you come to class you're prepared and you don't have to be copying these down. So in the last section we found the limit, and it said it didn't depend on what was happening at C because we were approaching a function. We'd have a function and it may have a hole in the graph, and we'd approach it from both sides, and it didn't matter that there was a value of C there, but we were looking for the limit, and so we would find the y value. That's supposed to be an L, and so we'd find that y value as we approach from both sides, and we did it numerically or with a graph. Well, we can also do this without those things. We could do it what we call direct substitution, that if we can get the function, if we can directly substitute that C into the function and get a value, we will get the limit that we're looking for. And also we may change a function to be able to find that limit, and that's what we were practicing last year in pre-calculus when we were doing removable. We would factor a fraction into its binomials and cancel out like binomials and things like that, and we'll talk more about that when we get to class. But just know that we can do direct substitution as another process instead of using a graph or a table. And so then some properties that happen here, that B and C are some real numbers, and so if we were going to do direct substitution, if we're approaching the value of C, but this is a constant, so we have a function that is a constant, say that's our B value there, and as we're approaching C down here from the left and the right, it doesn't matter if the thing's a constant. As we approach that C value, our limit will always be B. That should make sense. If we are looking at a function, in the second example, if we're looking at a function that is y equals x, which is basically what we're saying, x is our function, we would get a line, the parent function for a linear function, it would be y equals x, and if we are approaching a C value from the left and from the right, well then we would end up with C being our value, because for every x that I plug in, I get the same y value. And it also works the same for a function that has a power on it. Basically, it would be plugging in the C value, so that's our direct substitution. So make sure that you get these guys down so that we can be prepared for class. In the next one, these are all our properties of limits, and so basically what we're saying is that if we have a function f of x here that we are taking the limit of as we approach C, we get some value L, some number. And we do the same, some other function, and we take its limit, and that's supposed to be over here, as x approaches C on this function, then we would get some other value, k. So such things that happen are scalar multiplication. If we multiply the function L by something, then we are basically multiplying the limit by a value. If we are adding or subtracting functions together, well then we could take the value L plus the value of k, so we could just find the limit of one and then find the limit of the other and add them together, or we could add them together first and find the limit, and we'll get the addition or subtraction of those together. We could have a product where we will multiplying two functions together, and basically it's the same as finding those two values and multiplying them together. We'd have a quotient where we can divide them, which is the same as dividing those guys as long as one of them is not 0, the bottom one is not 0. And then also we could do powers, which is kind of like the last one that we just saw in the previous one, but make sure you get these guys down, and if you have questions about them, please come to class prepared to ask about them, and I will talk more and I will give you some examples and things like that. In the next one here, we are talking about a polynomial function, and a polynomial function, as you know, would be something like this: 3x cubed plus 4x squared plus 9x minus 74, or something like that, a polynomial function. And basically what this tells me is, instead of doing the limit individually, saying the limit as x approaches C of 3x cubed plus the limit as x approaches c of 4x squared, and so on and so forth throughout the rest of this problem. This is saying that we could plug c directly into those values for x and plug and chug and get those numbers, and we'll end up with a value that we could do. And so if it's a rational expression, we got to be careful, because if it's a rational, we have a fraction function, and it just depends so that the bottom is not equal to 0. And there will be two outcomes that happen of this. If the top and the bottom are 0, we're going to have to do a little more work. If only the bottom is 0, we'll know that this ends up being an asymptote. There's an asymptote there, and we'll talk more about that in the future also. And then it works the same if we have root functions. And so if n is odd, then we could just end up with something that looks like this. And if n is even, then c must be greater than 0. Because remember, if we take the cube root of a negative number, like -8, we can get -2. But it does depend that c needs to be positive, so this would be like the limit as, so this function right here as an example for an odd one would be the limit as x approaches, say, -2 of, or -8 of the cube root of x. Well, there's an odd power, so I could plug that in and I would get -2, but I couldn't do the same. I couldn't have a limit as x approaches -8 of the square root of x, because it doesn't really technically exist without imaginary numbers. So in this one, we in calculus we only deal with real numbers, not imaginary numbers for the most part, at least for this calculus that we're dealing with. So then we can have composite functions, and composite functions are kind of the same thing. Composite functions, we can either do the limit of 1 and find its value, and then do the limit as we approach that new value, and do it and do direct substitution into the second one and get an answer. Or we could do it all at once, and we could plug the two functions together. So this kind of gives us an algebraic option, and like I said, we'll be doing this in class. You know, you could do something like if g of x was x squared, and if f of x is, say, something like 3x. And so if we went f of g of x, then, and we wanted to find, say, the limit as x was approaching 2 of this of f of g of x, well, then I would say I could find the limit as x approach. I could do this in 2 steps if I like, or I could break it apart, and I could say, oh, I could do the limit as x approaches 2 of g of x, and find out that the answer for that is 4 by plugging in 2 here. And so then I would do the limit as x approaches 4 of f of x, which then would get me 12. And that would be the answer that I was looking for. Well, the other option is to do the limit as x approaches 2 of f of g of x, and that would be basically saying g of x into f of x. So that's the same as saying the limit as x approaches 2 of 3, and now I'm replacing my x in f of x with what g of x is, and that's the x squared, and doing a direct substitution that way. And so it's just options that we're giving you here, and you just kind of need to decide what's best for you. But you could see that this ends up being 3 times 4, or 12, which is the limit that I was looking for. And then we also have sine and cosine. All our trig functions work for this one, and we can do direct substitution into those guys as long as the c is in the domain, doesn't fall on an asymptote or something to that effect. So as I was saying, direct substitution works for trig functions, so just make sure that you can, we can test this out, and we'll practice this in class also, so make sure you get these down if you need them. In the next one here, we are talking about if we approach, so this is where I was talking about a function, changing a function to make it work for us. So for example, if I said that f of x was something like x minus 2 over x squared minus 4. Well, if I was doing a limit on this function, limit as x approaches 2 of x minus 2 over x squared minus 4, if I plug 2 into this, you will see that I will get a value of 0 divided by 0, which does not work for us. And so what this is telling me, what this slide is telling me, is that these functions are, that f of x could be written as a different function, say g of x. That would be something like x minus 2 over x minus 2 times x plus 2. I factored the bottom, and if I cancel out the like terms, which are causing the 0 over 0, g of x is a similar function to f of x, except for at the one point of positive 2, that was causing the 0 over 0. So now the limit as f of x approaches positive 2 is no longer giving me 0 over 0. This, if I do the limit of g of x as x approaches 2, then I would use the function that I changed to 1/4. So that means that this function f of x is approaching the same value of 1/4 as g of x approached, except for f of x had a hole in the graph, which basically means that I can remove it and do this. And so this is what happens if we have a rational function and we end up getting 0 over 0. When we do direct substitution, we can change that function to remove that point, that x minus 2 over x minus 2 that's causing the 0 over 0, and then do direct substitution on the new function. And that's what this slide is talking about. So make sure you get this down. Very, very important. There are the strategies that we have to go through it right now is basically direct substitution would be our first approach. That would probably be our best approach. If it doesn't work that way by direct substitution, then we may try factoring something out like we'll talk about in example 6. If that doesn't work, then we can do it with a graph or a table, and that's where we're headed with these guys. So make sure that you understand that we're kind of working on a system of let's try not to use graphs and tables as much as possible, but we sometimes need them, and then direct substitution or changing the function and going from there may be our best bet. And so then last but not least, we have the squeeze theorem. And the squeeze theorem is basically for us to talk about two different functions to find out the limit of a third function when we don't know exactly what's going on. So we have two different functions. We have h of x, which is this blue function on the bottom, and we have g of x, and we're asked to find the limit as x approaches c of f of x. But we notice that f of x is in between g and h at all points. Well, if that's the case, then the limit as g approaches c is this value L, and as h approaches c from both sides is also this value L, and since f is in between them all the way, that would mean that this f is squeezed in between, and so its value is also L, whatever that number may be. And this is very important for one of our two trig properties that we have in this unit, so we will talk about those, but make sure that you get the squeeze theorem down, and these are the two special trig functions that go along with this. And we can talk more about this when you come to class, so please get the squeeze theorem down and get this information down, and we will talk more when you come to class. So please be prepared, and I look forward to answering your questions and working with you in class. Thank you.